Hello, everyone. Welcome to this new event of the Under 40 lecture series on combustion. It is my great pleasure to introduce today Dr. Rachel Schwind. She's a lecturer in experimental thermofluids at the University of Edinburgh. Her expertise in reaction kinetics and complex phase change, and she has a focus on non-reactive materials, high-pressure chemistry, with applications in a broad range of fields going from waste to energy fuels, material synthesis, and energetic materials. Now, prior to joining the University of Edinburgh, she was at Brown University, first as a postdoc and then as a senior research associate, where she oversaw the experimental activity in the Goldschmidt Lab for Chemical Kinetics. She has received her MS, Master of Science, and a PhD in Mechanical Engineering from the University of Michigan. And at the time, she also had a grant from the US DOE to serve as a visiting researcher at Argonne National Laboratory. So today, Rachel, we talk about from space propulsion to nanomaterials, exploring the role of experimental reaction kinetics in fueling a sustainable future. Rachel, thank you very much for having accepted the invitation. I give you the floor for your lecture. Thank you.
Thank you for inviting me, and thank you everyone for attending. As just stated, I will be talking about from space propulsion to nanomaterials, exploring the role of experimental reaction kinetics in fueling the sustainable future. The goal of my research is to use experiments and novel analytical methods to bridge the gap between fundamental chemical calculations and complex operating environments. So the idea is to really look at how we can bridge that gap between looking at something like a calculated potential energy surface. This is a representative one for isopropyl nitrate from the Goldsmith group at Brown University. To, okay, what happens if we take that liquid propellant and put it in a rocket engine? How can we go from one to the other? Or maybe looking at oxidation pathways for hexamethyl disiloxane, calculated by my colleagues at Argonne National Laboratory, into how it plays its role as a precursor in nanoparticles for silicon-based nanoparticles, battery materials, and things like that. The idea is taking all of this information from multi-phase environments, looking at fundamental ignition delay time studies, modeling, and fundamental calculations to build comprehensive mechanisms and models to further our understanding of complex behaviors and advanced technology development. How that process works? Well, looking at fundamental experiments and observations in complex reaction environments. So that could be something like looking at changes in specific impulse for a propellant candidate, or maybe looking at what we observe in an engine study or a high pressure liquid fuel burner. We can isolate key drivers for further interrogation. So if we're looking at things such as, is it a phase dependent, pardon me, is it a phase dependent transition, or is there a key reaction that we need to be monitoring to then look at and isolate those kinetics in further detail? We then model the key results for fundamental kinetic insights and then start filtering that back up. Can we capture the behavior of the isolated compound? And then what happens if we actually put it back into these larger systems? Do we need to reduce it any further so that we can better introduce larger scale models? And in that case, what is key to capture the actual behavior that we're observing? So I'm going to walk you through kind of how we do that, the link from the fundamental to the more applied for these compounds. And what I'll start with is a propulsion simulation. Sorry, not simulation, scenario. So I'm going to be talking about liquid nitrates. And for those of you that work in the propulsion space propulsion, a lot of you look at hydrogen, you look at methane. So why are we looking at liquid nitrates? What makes them so interesting other than, well, I've got a really cool video of isopropyl nitrate at 34 bar in air. One of the things is the stable liquid propellant candidates are ideal for minute control and positioning. This is if you just need to slightly change a satellite in space, or if you're looking at smaller satellite launches where you need to have something that is stable on a launch pad, where it can sit for a long window of time so that you're actually looking at being able to sit there for a while without needing cryogenics like you might for hydrogen or methane. Additionally, they have high specific impulse monopropellants, so no external oxidizer is necessary. If you look at the structures here, they actually come with their own oxidizers built in with those nitro groups. This then reduces the size of your payload. You save space and weight for your payload by reducing the amount of space you need for your fuel and oxidizer tank. They're highly pressure dependent, which then makes it a little bit more interesting as we start to look at the interplay between the chemical and physical behavior. We start to move towards transcritical conditions, which can make it a little bit more complex to understand and go forward with designs. The current standard, we've been using it for a while, is hydrazine, but unfortunately it's highly toxic. That makes it an ecological concern if we have to leave it sitting or if we have any spills, but then also for anyone that needs to handle these systems. So the idea is we want to find reduced toxicity monopropellants that are also still stable, and we can use them going forward. Additionally, as I mentioned, there's currently a limited understanding of that physical and chemical interplay. What happens as you go up in pressure and you start to transition towards critical states? What do you see as these two things start to blend together? So what did we want to do? The idea was we start small and then work your way up big. So if we're looking at nitromethane and ultimately we want to look at a larger nitrate ester like propylene glycol dinitrate, we're going to have to start down here because the small molecule chemistry will be relevant to these larger molecules. So if we haven't quite figured out what's going on down here, we're going to end up kind of with a mess if we try to start modeling this. We can also then start building class rules as we start to look through these structures. You look at isopropyl nitrate, it's relatively similar to propylene glycol dinitrate. There's a slight nitrogen group change. So we can build structure and class-based rules for this. Additionally, if we're starting with nitromethane, which will be the focus of the research that I'm going to highlight today, it allows us to benchmark it against something that we have a little bit better of an understanding of before we start moving to these more exotic fuels. And then we can make sure that our methods and our correlations are valid with something that we understand better before we start trying to guess. So we have that chemical blueprint. Now we need something to measure. So the idea is we want something that we can use as a reaction marker for intrinsic behaviors that we can target for modeling. This is where looking at pressure-dependent burning rate behavior is valuable. It provides an avenue for benchmarking performance and models. Generally, we look at St. Robert's law to provide a correlation for burning rate as a function of pressure. This is also a carryover from the solid propellants community, which they usually do this in strand burners, and you can develop different understanding of different combustion regimes based on where these slope breaks occur. This is somewhat kind of representative of what we might see for something like nitromethane. And one of the things I want to highlight is these slope breaks don't necessarily occur where we might intuitively expect them based on phase behavior. The critical point for nitromethane is somewhere just around 8 megapascals, but generally our transition for switching the burning rate regime is actually at 14. That was proved by the group at Penn State. So it also gets us help understand what these fundamental behaviors are. So now that we kind of have a performance metric, now we need an experiment to measure it. And that's where we look at the liquid strand burner. This was previously commissioned at Brown University. It has since been decommissioned, and we're in the process of redesigning and bringing one online here at the University of Edinburgh. But briefly, how this works is we have a high pressure chamber here that is continuously fed with our diluent gas. This is nitrogen for when we're actually operating it as a monopropellant. We don't want oxidizer influence, but we can actually swap that for air if we are interested in understanding the influence of the oxygen. This goes through and is continuously fed through with ports on our windows. And a back pressure regulator allows us to maintain a constant chamber pressure. This allows us to have a high pressure environment, but still have a continuous exhaust so we don't build up volatiles and don't end up with secondary ignition maybe in the exhaust stream. It also allows us to have that continuous flow of diluent so we aren't building up potentially toxic emissions. Unfortunately, with anything that has hydrogen, carbon, and nitrogen, you are going to be producing some things like hydrogen cyanide. So we're keeping those relative concentrations low on our outstream. We then provide the liquid fuel so that we can have a burner stabilized flame at the mouth through a pressurized tank of nitrogen on the back side. Pushing this through, we then go through a differential pressure gauge and micro orifice up and then into the chamber itself. This is steel tubing, and then at the interface here, we actually switch to quartz so that we can observe some of the behavior of the liquid prior to the combustion region here. And also it prevents us from having any catalytic effects by having the metal within the system. We have a nichrome ignition coil wrapped around the quartz that allows us to provide ignition energy so that we can heat heat the liquid propellant up until it vaporizes, and then continue to provide heat energy to allow for the ignition. This is unique to this burner compared to other traditional strand burners that have also operated as liquid strand burners, where they actually use a draped nichrome coil. This allows us to actually provide more heat energy than any of the other models, so then we can actually achieve ignition where other burners have not been able to. Our differential pressure gauge here measures our flow, which then provides our burn rate. Anything that goes through here has to come out through here. If our flame isn't moving, which we can monitor with a webcam, we know that then it's got to be burning. So we can correlate that directly to our linear burning rate, and then also monitor for flame stability as well using the online webcam. So a look at our burning rates for nitromethane. Our results and the correlation are here in blue, and then other studies as well. What I'd like to highlight is we are within bounds. Each data point is the result of averaging over 1 minute of operation because we have that continuous feed. We aren't measuring its propagation down the tube like you would observe for a what we refer to as a static liquid strand burner, where it just burns down the quartz tube. That does introduce a little bit of play because there is another the only other continuous feed system here is from Boyer and Kuo out of Penn State. And those two both predict higher burning rates than the ones that are static strand. We have two hypotheses for this. One is that we don't have heat transfer into our quartz because we're able to maintain it at the mouth of the quartz. So we're able to maintain that heat energy a little bit higher. But also because we're bringing the fuel to the interface, we're able to potentially slightly create a condition where some of the vapors might somewhat escape, whereas they're a little bit trapped and recirculated for some of those exhaust gases and things like that in the static strands. The only other thing different is we were able to ignite down at 4 and 5 megapascals, which was difficult in other studies where they actually used a slight concentration of oxygen to start, and we did not need to because of the additional heat energy we were able to apply through our coil wrapping. And then also some use starter pellets, or what we refer to as squibs, to basically provide a small explosive starter to that. So we were able to benchmark that we were within reason. We were able to measure these burning rates. They behaved as we would expect from literature. So now we wanted to figure out how we could use these measurements. We wanted to link what we can measure and what we can model. This is where basically the two things we were looking at is we didn't want to have to model the entire system. That would be extremely computationally expensive. And then we run into the complexity of the fluid mechanics model would reduce the fidelity with which we could understand the kinetic model. So the idea was to identify two different things that we could look at using Cantera, laminar flame speed, or 1D burner stabilized flame, to look at correlations to linear burning rates or species profiles. But it isn't quite that straightforward. So here I'm going to highlight our burning rates and laminar flame speed. We do have some species profiles. We're still in the process of producing the data and analyzing all of that in collaboration with Montana State. So I won't be going into that data before, but please be on the lookout. We've got some interesting stuff coming up on the horizon. So for the linear burning rates to laminar flame speed, we want to figure out how we can correlate these two. How do we go from our traditional purely gas-based linear burning, laminar flame speed to a multi-phase linear burning rate? Generally, when we look at laminar flame speed as a function of chamber pressure, we're going down as we go up in pressure. There are some different cases, but for the most part, and for our predictions with nitromethane and isopropyl nitrate, that's what we observe. However, as I showed previously, burning rate goes up as a function of pressure. And one way that we were able to actually capture that behavior is by accounting for that phase difference between the burned gases and the fact that we were starting with a liquid. When we use that correction through the ratio of the burned versus the liquid propellant, we actually do get the right phase behavior, trend on that. But for the laminar flame speed versus the actually measured burning rates, we're still off by at least a factor of 10. So that leaves us with three possible modeling errors: the underlying kinetic mechanism, the correlation between the experimental burn rate and laminar flame speed, and the temperatures used to define the conditions. Well, looking at how we've kind of started to set this up, the underlying kinetic mechanism for nitromethane has been relatively well validated to high pressures. So we're thinking if there's errors there, we might be able to validate them slightly and improve some of those rates. However, not to the extent that we're off by a factor of 10. So for right now, and the fact that we know we're just kind of looking at a simple ratio correlation here, we're going to say that that's not our problem. So then the next thing we want to look at is the correlation between the experimental burn rate and laminar flame speed. So as I mentioned, when we're looking at this initial ratio correction that we did, it gave us the right trend-wise behavior, but it wasn't on the same scale. So then we looked at literature and found another correlation used by Penn State in a collaboration between Penn State and Yale that relies on the assumption that the liquid surface temperature and the ignition temperature are the same. We used that, and so here are experimental points here, and then two different corrected fits where we did not add the heat source term, we just added the corrections of the specific heats, and then we did I did add in a source term, and then we at least got on the same scale, but we weren't capturing our higher pressure data. So we had a significant increase in the percent difference as we increased pressures, which then told us there might be something that we're maybe overlooking. So we went back and looked at the temperatures used to define the conditions. Right now, we're somewhat approximating what that might be. So when you expand out take away the assumption that the ignition and the surface temperature are the same, you get a much more expanded equation. Now, we did have some justification for why we wanted to do this. Initial testing when we were working with nitromethane here, so I've got what we refer to as a flame inception temperature here and a chamber pressure here. We took some measurements with a thermocouple in the fuel line where we looked at the approximate temperature inflection point when we were able to observe ignition. Because we couldn't control where the ignition occurred relative to the tip of the sensitive area of the thermocouple, we can't call this an ignition temperature. But what it told us within relative trend-wise repeatability was that we did have a difference in net energy in the system when we were igniting with nitrogen as our environment, which is these orange diamonds here, or if we had air as our environment, which is the blue here. Air almost demonstrated a insensitivity to the pressure changes, whereas nitrogen, we saw a significant difference. This told us that there were different pathways, and also that if it was purely a phase-driven property for ignition versus that surface temperature, these should be the same. So then if our phase change and ignition are actually at different temperatures, well, this tells us that there might actually be something wrong with that assumption. We decided to further interrogate how we might actually estimate what the surface temperature could be by looking at what the vaporization temperature might be. Now, this is another one where we had some limitations within how we were able to do the measurement. And again, with the thermocouple in the fuel line, using a slower heating process, we were able to look at the temperature at which we started to vaporize, and we were able to measure that. What we found was trend-wise, we had similar behavior. So we were presented this initially at the US National Meeting. The lines here are actually using the Antoine coefficients and expanding them out. We have to extrapolate those from much lower pressures than what we're actually working with. And then we also have the reported critical points here. We then repeated our experiment from the US National Combustion Meeting 2 more times to get a better data set and to also see the repeatability. What we saw was a repeatable trend, but not a repeatable temperature. Currently investigating how we can better measure and control this temperature and heating process through a better data acquisition and control system. But for right now, we found that consistently we were below where we thought we should be based on the Antoine coefficients and potentially below the critical point, which might also help explain, as was identified in a study out of Penn State, subcritical burning behavior at what should be above the critical point for nitromethane. So with that in mind, we started to think, okay, we need to find another way to look at this ignition temperature and the surface. We need to be able to use the entire equation that we have here. And unfortunately, based on these measurements, we don't have an exact number, but we can get approximately close with what we're doing. And so with that, we did a numerical analysis using Cantera, adjusting the surface temperature here, and then initially maintaining an ignition temperature, but then also varying that slightly based on the ballparking with the results that we previously had, and found that if we decrease the surface temperature as our pressure increases, we are actually able to capture this behavior. So for right now, this is a numerical exercise. We're in the process of doing higher fidelity measurements so that we can actually get a better approximation for that surface temperature and validate these results. But we're relatively interested in finding this out. The other potential aspect of that is because this could have implications for both chemical reactions and defining phase behavior. So our surface temperature can give us key insights into the chemical and physical interplay. If our surface temperature is below our vaporization temperature, as has been proposed for nitrated esters, with the caveat that this has not been conducted for nitrate esters since 1955. So we would like to revisit some of those measurements with higher fidelity measurement techniques. Our phase change is chemically driven, or our interface composition is not what we think it is. So we could either have condensed phase chemistry that is driving forward that producing our gas phase species, or we have an interaction between radicals abstracting from the liquid fuel and then producing two gas phase species from that. So the heat transfer through the liquid or solid, as I mentioned, can drive condensed phase chemistry. That is one of the proposals in solid propellants from double base propellants. This is from my colleagues in chemistry here at the University of Edinburgh, looking at how we can understand the reaction processes for solid propellants. Then both of these processes will be dependent on and drive the gas phase chemistry. We then can figure out how much heat we might have coming back based on the combustion reactions occurring at that interface, but then also what is happening ahead of the interface will tell us what's going on. So what about that gas phase chemistry? That's where I started my career. So I'm going to start talking about how we isolate and study that at flame relevant conditions. One of the easy ways is you build a shock tube. So this is the brown shock tube. This is different than your traditional shock tube. So we do have a driver and a driven section. Traditionally, these are separated by a diaphragm. However, for the Brown system and also the Argonne National Laboratory system, it is actually operated by a fast actuating bellows. And this rapidly pulls back, introducing your high pressure driver gas into your driven gas. This produces a highly repeatable shock, and when the driver and driven gas meet, you generate a shock wave, which instantaneously raises the temperature and pressure of your test gas. Then as it propagates down, it will hit your end wall and bounce back and give you a reflected shock. The idea is you can actually do measurements either in the incident or the reflected shock. With the reflected shock, you get a second heating, and you freeze the particle motion. In the incident shock, you can get very high temperatures and very fast kinetics, but you have a very small window to measure this in. This hopefully gives us the temperatures we need to induce fundamental gas phase reactions. And I'm actually going to be focusing on a unique technique that allows us to actually look at things in the incident shock. So hopefully once we have that initial pass through, we've raise the temperature enough that we induce thermal decomposition, and then we can measure that reactivity with a technique referred to as laser Schlieren densitometry. So across the observation window in the shock tube from the previous slide, we have a continuous wavelength diode laser. So we're currently using a 632 Fabry-Perot. You can use a Heaney. It's centered on a 4-quadrant detector. And then as the shock wave passes, that'll induce a density gradient because you're instantaneously heating, that gas. And then that change in density and also just the shock wave passing will induce a deflection across the 4-quadrant detector. And we can measure that, which will then correlate to this density gradient. Now, as the shock passes, it will relax back down. But sometimes that doesn't occur, and you actually get some interesting behavior in this relaxation. That occurs because you actually have heat of reaction and changes within your chemical composition inducing this density gradient, not just the excitation of thermal excitation. And that's what we're interested in. We can then use that to inform our kinetic models. So this is a representative figure, thanks from Fuller et al. Work at Brown, provided by Franklin Goldsmith. So we have isopropyl nitrate, 730 Kelvin in a bath of krypton at 69 torr. So what we can do is look at this induced density gradient and model that based on our reaction progression, using the heat of reaction as well as the changes in the composition to model this behavior. And uniquely, we can capture the first 10, 12 microseconds. One thing I will note here is we've got time in microseconds and the log of the density gradient. Because they log plot, we can't actually go negative. So this turnaround point is actually where the density gradient goes negative, and that can actually give us a lot of information. So not just can we model this, but we can also get insights into the reaction energetics. One, we can identify reaction regimes. We can identify different things such as where the reactions will actually occur, because we know where we start to see signals. So we can identify activation energies, things like that, based on the temperature at which we start to observe reactivity. The other side of it is we can actually look at thermic behaviors. So looking at where we're net endothermic or net exothermic, and then we can better understand how these might contribute to a broader system, where we might need initial energetics to start going and where they might be self-driving. So I want to look at this as at the chemistry of a key intermediate for IPN combustion, acetonitrile, and walk you through that process. So the first question we have is, do we see reactivity and where? So here's our compound acetonitrile. We're also interested in this because it is occasionally shipped with nitrates in order to stabilize them. So we also wanted to identify where it started to decompose so that we could stay below it, or if we understood its reaction contributions, we could filter it out in signals where we weren't able to stay below the reactivity. The good news is it's relatively stable up to relatively high pressures and at low concentrations. So we really didn't see any reactivity there until we increased the concentration slightly to 4% and then went above 2000 Kelvin. And we still didn't see a lot of signal, but we were at least getting something. So then we wanted to look at what are our mechanistic options. We identified 3 different mechanisms from Lifshitz and Tambaru, Sent, Aikita, Baxi, and Mackey, and then Alzueta is the most recent one from 2021. 2 of them were shock tube ignition delay time and shock tube pyrolysis studies, and then we have a flow reactor oxidation study. These 2 both only identified an H atom ejection initiation, whereas the updated Alzueta model included also bond scission to produce methyl and CN. Worth noting also is that the study from Mackey's group also included ab initio calculations, and based on those, discounted the fission to CH3 plus CN, elimination of HCN to form CH2, and elimination of H2 to form HCCN. The bond scission channels also the elimination of those does also somewhat correlate with what we were observing. CH3 or CH2 would potentially have high recombinations, so then we would maybe expect to see a lot more exothermicity in what we're looking at. So then we looked at how well do they capture our experimental data. We only used the Sent and Alzueta because the Sent was actually an updated version of the Lifshitz and Tambaru mechanism. And what we found was both of those systems overpredicted our reactivity compared to what we were able to model using I think we're at 9 reactions there. I need to put numbers on that, my apologies. They overpredicted it. One thing worth noting though is none of those studies could actually measure within the first 10 microseconds, and they both contained oxygen. So this might just be a simple overprediction of the role of the initial thermal decomposition and maybe missing a branching ratio where it should actually be more attributed to interactions with oxygen-containing radicals or something like that. We're not 100% sure. We also had not only shorter time scale of observation, we also had higher temperatures. So again, these things would contribute to differences in these initial timescales, whereas the longer timescale experiments would potentially capture this quite well. So that's kind of the process for when we do know what we're doing, but what if we don't actually have a known or valid mechanism? And this is mostly because I promised I would get to nanomaterials. So now we're going to move over into the nanomaterials portion of things and kind of showing how we can use these very similar techniques in completely different environments. So the idea is we're using this more as a way to leverage energetic insights in larger combustion studies. And what I'm briefly going to go over is how we started with biogas and siloxanes and got to nanoparticle synthesis. So we're looking at two representative siloxane compounds, hexamethyl disiloxane here. So we've got two, what we refer to as trimethyl silo groups, bounded by an oxygen to create a silicon-oxygen backbone. And then trimethylsilanol, which replaces one of those groups with just an H, rather than the terminating trimethyl silo. So initially, we were looking at this when I started at the University of Michigan because they were contaminants in landfill gas. So if you're making the gas on site rather than flaring it or getting rid of it, because it has a high methane content, so that is a very potent greenhouse gas emitter, we'd like to be able to use it, especially because it's already part of the carbon cycle. So it's potentially carbon fixing if we can reduce that methane content to being CO2 and then something that we could capture. The problem is when you have these waste to energy fuels, you end up with everything that is also in your waste. Siloxanes are kind of in pretty much everything. The good news is they are not like our PFAS and PFOA that all of us are looking at right now, as in they're extremely benign. They are not a detriment at all to human health. However, they are a detriment to your engines. Generally, your engines don't like it if you have sand in them. So this is what happens when you burn in the presence of those. Now, I mentioned earlier in my talk that these are actually used as precursors as well to produce these particles for battery materials and other silicon-based products. So in one case, we're interested in making it, and in the other case, we really don't want it. But at the end of the day, the process by which this occurs is still relatively the same. We've got a small amount of this precursor or this contaminant, depending on how you're looking at it, in a bulk fuel, and it's producing nanoparticles. So the underlying chemistry is largely the same. It's just in one case, we want to promote and control what we're doing so we get those high value materials out. And on the other side, we're hoping to stop and interrupt that pathway. Now, one way we were looking at this was understanding the combustion influence. We wanted to identify where it actually had an influence and where it would be producing particulates, so you can then kind of put in standards of what is an okay detectable limit. And we found something interesting, though, by looking at rapid compression facility autoignition experiments. So we were looking at, this is our end of compression event, baseline composition of CO and H2 to produce a semi-syngas mixture with 100 parts per million of HMDSO or 100 parts per million of TMSO. So we have the end of our compression event that then creates an autoignition. And this is our baseline. Then when we looked at the two with contaminants, we had almost double the energetic release with only 100 parts per million on a full mixture basis. For our fuel mass basis, that was like 0.25%. We saw significant increases in energetics here. So a highly exothermic process going on to produce this. We also saw a decrease in ignition delay time. So it was happening rapidly. Well, combustion probably acts like a cetane enhancer. Everything falls apart. We're producing radicals. That's what's going to get us there. Unfortunately, that is not what, when we tried modeling, that didn't happen. So we thought, well, it's probably still falling apart, but it's something to do with these silicon compounds. Let's figure that out. And that was when I put in a proposal and was able to get approval and funding from DOE to then go work at Argonne National Laboratory and look at shock tube pyrolysis experiments. Again, using this laser Schlieren densitometry. So we're looking at the first 10 microseconds, our d-rho dx here. And well, we found that it was pretty much endothermic decomposition, and it was relatively stable below 1400 Kelvin. And if you look at our scale on our temperature plot here for our autoignition study, we were below 1060 for pretty much all of our experiments. So this basically told us these rapidly decomposing couldn't be the driving factor because it was happening on such a quick effect in our oxidation studies. I will note condensed phase production can be significantly exothermic, but on the timescales we're looking at, it still doesn't explain our results as to how this was occurring. So what that told us were there were two different reaction networks. the fuel oxidation chemistry. I'm not going to get much into this. We did first highlight this as a potential in our study published in 2019. We're still trying to unravel this. It's unfortunately a very large system, and our radical species are actually quite stable. But basically what we found was the most likely we had this influence of these fuel radicals that were abstracting a hydrogen atom, producing a radical species, and going through RO2 to QOH. Then we had to look at the thermal decomposition. And that's where we had a little bit simpler, in some ways, reaction mechanism, but we really didn't know what we were seeing. We were able to look into literature. We also just used the initial guesses that we had, which was an H ejection pathway or a methyl pathway, and then also direct molecular channels as well. But we don't actually know what species we're producing. We just have these species insensitive diagnostics. We've got global measures. So if you don't know what's there, how can we find out? That's where time of flight mass spectrometry can help. So there are two different shock tubes in the Tranter lab at Argonne National Laboratory. We have molecular beam sampling on both, directly coupled to time of flight mass spectrometers in the two shock tubes. This is the same shock tube as the laser Schlieren. You just open a gate valve on the end, and that is directly coupled into a mass spectrometer. We're able to do electron impact ionization using that. We then have a miniature shock tube or high repetition rate shock tube, and occasionally we refer to it as a baby tube because this is less than 1 meter long and can sit on a bench top. The idea is that it allows us to put it on end station at the advanced light source for the chemical dynamics beamline, and then we can use high vacuum ultraviolet light into the time of flight mass spec to do photoionization. That allows us to use very low ionization energies so that we can actually, and highly tunable, so we can identify different compounds based on ionization cross-sections. We have the high repetition rate where it actually is operated by a solenoid valve and can operate at 1 hertz. That allows us to run batches of hundreds of shocks at a time. So then we can actually maintain a high repetition rate to then do signal averaging. Since we have the lower signal, then we can still get information out of it. So if we look at the spectra, we can see a forest growing. One of the advantages to this also is we get everything that comes out. You can call that an advantage. You can also call that a disadvantage because then you need to sort through it. So we don't need to, if we're using targeted laser diagnostics like absorption spectroscopy or laser-induced fluorescence, we need to know what we're targeting. Here, everything's going into the mass spec. It'll get hit with ionization, and then we can use its flight path to determine the mass that we're looking at, or our M over Z. So these results are from 28 to 30 EV using the diaphragmless shock tube, averaged across 10 shocks. This is our standard based on NIST. So we have our main peak at 147 here. We are using argon and neon as our bath gases because those provide a good internal standard and still produce strong shocks. What's worth noting is pretty much all of our activity is at the lower masses. We don't see growth to higher mass silicon species. In fact, we really don't see any silicon species at all. So here we're looking mostly at organics with 26 and 28, 16. Hydrogen comes in at a very early time, so that's helpful. We did also confirm that that was hydrogen by going out to longer masses and making sure that it wasn't just a higher mass hanging around from the prior ionization. Worth noting, though, is because we use these internal standards, anything that would be appearing at 40, we cannot observe, as well as neon obscuring anything in the 20s. So that gave us some information, but we also couldn't, although we were pretty sure that the 28 was not ethane, we really didn't see any signs of that. We needed to be able to actually identify specifically what that 28 peak was because so many organics do actually appear there. Where's the silicon going very quickly? On the end wall of our shock tube. Like I showed you in the engines, we produce silica particles. We do in our shock tube as well. So that did tell us, okay, we are getting some condensed phase behavior here. Unfortunately, we can't analyze this because we can't really correlate it to a reaction progression and the number of shocks contributing to that buildup. We can't kinetically say what that is, but we can identify we're definitely putting some sand on there. So then we started looking at the experiments from the advanced light source, so 1580 Kelvin, 12.2 atmosphere, and this is 12 to 7.5 EV, 100 shocks in each EV range, 18 steps. meaning 1800 shocks sum averaged. However, because of the different ionization energies, this is going to be mostly signal dominated by what's happening at the 12 eV and those higher ionization thresholds. Worth noting, we have an argon gas filter in the line, which should filter out any higher harmonic light above 15 eV. And so we shouldn't be able to see our lovely argon peak here, but we do, as well as oxygen here at 32 and then water at 18. So we were getting higher harmonic leakage on that high vacuum ultraviolet light. So that did create some issues when we're trying to identify some of these species because we're starting to see peaks that we maybe shouldn't. The way to adjust that is to use what we refer to as a mag fluoride window filter. So that will filter out anything above 10.5 eV. And now we've lost all of these masses down here. So that lets us definitively identify that the 28 is ethylene. And then we still see our 40, 41, and 42. What's interesting to note, one of the things that we've noticed with all of these, so if you look at the 147, 148, 149, which is part of our parent, we generally see 3 peaks within our silicon compounds because they contain common isotopes of silicon at 28, 29, and 30. So this really helped us because then we could start identifying silicon carbide. So we looked at the photoionization cross-section and we're almost bang on for what was predicted. So we're pretty confident that this 40 is actually silicon carbide, and that has not been previously identified as the decomposition product for HMDSO. So first identification of that. Additionally, we could look at this 75 peak here and identify it. We do not have information for trimethylsilanol. There is no existing cross-sections for it. However, we ran trimethylsilanol experiments as well. So we could take that signal from those experiments and actually look at that same mass peak. The scales are going to be different because one of them was pure trimethylsilanol and the other one was, it is a potential product in a larger system, and basically got the exact same shape. So we're now pretty confident that we have now also been able to identify trimethylsilanol for the first time in that. But now we've still got all of these peaks there. So one of the things that we would like to do, because some of them have similar mass peaks, any of them that have a trimethylsilyl group will produce a peak at 73. So I've developed a technique to filter out the influence from the parent molecule or contaminants, because we also found our HMDSO was a industrial production contaminant in our trimethylsilanol. So we wanted to be able to filter those out so that we could see what was happening underneath it. Once we did that, we could start seeing some of the more underlying peaks relevant to products, such as this M/Z at 73, giving us tetramethylsilane. Still need to refine this a bit because there are other things that could be there, but we are seeing a significant change right in the range of reported ionization energies. We have just recently also been able to potentially run some PIE scans of tetramethylsilane, so we might get more information on that in the coming, because we just were able to run some experiments this past summer and we're still sifting through that data. So let's go back to that potential reaction network very quickly. HMDSO, we've got a couple of these pathways. What I didn't say before was thanks to Raghu Shivaram-Krishnan at Argonne National Laboratory doing potential energy surfaces for me. Those are energetically inaccessible with both in our oxidation studies, but also in our studies in the labs at Argonne. But as I highlighted, we're able to identify for the first time tetramethylsilane, which is here, using as a reaction progression, coming in at a very quick, relatively early on here, and seeing a similar thing for the trimethylsilanol as well. And then also here, as you can see, it's a bit sketchy, but we filter out the parent peak at 73 as well. Then we have these two highly reactive intermediates. So unlike carbon, which this would be a relatively stable species, these are actually highly reactive in the gas phase and most likely won't even last the 10 microseconds for our pulse plates to get into the spectrometer. So we haven't been able to identify them. However, we can look for their decomposition products. So silicon carbide shows production behind the start of the TMS and TMSO. So we see that slightly lagging behind it, which gives us a good indication because that is a proposed product from the dimethylsilanone, which is this one here, and the 2-silos butene. C2H4 also displays similar behavior, which is also a proposed product for these highly reactive species. So we're starting to really build that we might be able to see these. From our other experiments, we also see H2, C2H2, and methane are also proposed products. Unfortunately, we can't correlate those directly right now just because of some slight differences in the data acquisition, but we're hoping to resolve some of that and be able to look at the relative timings of those appearances of those peaks. And if they still lag behind the co-products here, we're feeling pretty confident that we're producing these and getting some stability in those secondary pathways. And then hopefully we can use that information to help us then continue modeling those laser Schlieren decomposition peaks. So wrapping up, how does all of this work together, kind of run all over? The global studies allow us to understand the role of chemistry in dictating the system behavior. We can then isolate the key chemical drivers for fundamental interrogation. We can then also understand which aspects they might be driving, so then we can give representative. If you only need a heat source term, we can maybe come up with something that might work and can be put into a larger model, rather than giving you an entire hundreds of reactions and species kinetic model that will basically completely bog down your solver in your fluid mechanics. And we can just use that continuous feedback, ensures that we constantly improve each phase. So are we accurately modeling the fundamentals for this one species? And then does it actually integrate back in appropriately with the larger mechanisms and operation? We can then identify targets to improve performance and technology maturation. Is it more worthwhile for us to target chemistry, or is it more worthwhile for us to look at new designs that might introduce new fluid mechanic effects, or some combination of the two? And then a bonus that I always like to include, it's an excuse to have fun playing with physics and chemistry, which is why I still keep doing it. So just quick acknowledgements to everyone who supported the various aspects of this work. All of it is still ongoing because we've kind of just cracked open quite a few of these in recent years. The group at Brown, Office of Naval Research, Walker Research Group, my colleagues at Michigan, and Argonne, as well as my various funding agencies as well. So thank you all, and I'm very happy to take any questions.
Thank you very much, Rachel, for this very nice talk. I open the floor to questions. Let's see where people maybe warm up. I was wondering, and this is, I mean, chemistry, I understand, the basics, but not my research field. So I was wondering, there are some exotic molecules that you study. So the kinetics for that, do you get them by analogy or some theory? I mean, what is the approach that you use in that case?
So some of it is we just kind of go on a big hunt and see if somebody's come up with a mechanism. And specifically, one of the big issues we're running into right now is isopropyl nitrate, which actually I was fortunate to be working with the Goldsmith group. They had done some of the theory and chemical calculations there, and had developed a mechanism in collaboration and building off of a lot of with CNRS in France at Orléans, and then also building off some of the group Peter Glarborg had done. And then we found that it falls apart at high pressures. So what we're kind of doing is looking at what exists, seeing if it works and we just need to tweak it, or if it breaks, do I need to ask my colleagues in chemistry very nicely to do fundamental chemical calculations for me? And so then that's where, as we were seeing with the silicon chemistry, that was actually very dependent on getting buy-in from my colleagues at Argonne to do some of those calculations for me. And that one is a much slower process because we're still unlocking that. We get really excited when we can find an analog. We tried DME, dimethyl ether, and it did not work. So we quickly found out the carbon analogs don't work for some of these more exotic somewhat metallics. And on the nitrate side of that, we're trying to figure it out what might be there. There's been a little bit more work in nitrated chemistry. But silicon chemistry, we don't quite have as much information. And then I didn't go into it. I've been involved also with some fluorocarbon stuff, and that has seen actually some advancements in using things like RMG. And we do occasionally try to take advantage of those tools. we just run into, those are kind of reliant on what data sets are out there. So sometimes what we find is it doesn't exist because no one's done the experiments yet. And now we've done the experiments, so we need to kind of restart the process again. So
I guess it's also a way to kind of infer if you know, there is the need for more fundamental research on the pathways that, or like steps that were not explored. So in that sense, of course, it's a continuous learning process.
yeah.
I see if there are questions. So maybe Marco will.
Okay, but you hear me from there? Can you hear me?
Can you hear Marco?
Barely.
I can.
No, Rachel, I was wondering. Obviously, it's clear why you were doing the studies on the nitromethane, etc. But there are some many actually industrial processes that use nitration reactions to produce chemicals like pharmaceuticals, etc. And I think similar reaction, exothermic. So I was wondering if your studies have a broader impact in this sense, because it can be really obvious, because in those kind of studies, they use very, very simple global schemes, while instead you manage to provide much more detailed information. So yeah, that was I was wondering if you ever thought about that.
Honestly, no. I'll say that from the perspective of we hadn't really explored it because, well, somewhat was our funder was very interested in us moving up towards the larger species. So part of the nature of research sometimes is just keeping your funder happy, but also I think it is worth exploring. I would just need to find out more about the processes a bit more, because I'm not as familiar with that side of the chemical industry. I'm more on the nanoparticle side of things. But I definitely think there could be opportunities. I would just need to know a little bit more about the fundamental processes on it before I could comment about what would carry over and what might not carry over.
Yeah, thanks.
Thank you. I'm looking at the chat. If you don't wanna ask the question, you can also type it. I can read it. Let's have a look if anyone else. Okay, seems that there are no more questions for now. In that case, I would like to thank Rachel again. Thank you very much for this very nice talk, and I thank all the people who were present online. See you for another event of the series. Thank you, Rachel. Have a nice weekend.
Yes, and thank you for having me.